So there's this GPU framework I've been developing for a while now, and oh wait, how long ago was that? 3 years? Oh boy, let's see what I can do. My main motivation for this framework was to have something that really lets me focus on graphics programming algorithms, instead of getting frustrated with all the resource management and boilerplate code required by modern low-level graphics APIs. Or fighting some game engine when I'm doing something a little bit custom, not covered by their abstraction. And according to this post on Reddit, I'm not the only one who feels that way. Another aspect that always annoyed me is that in all other areas of programming, there exist a million libraries that provide solutions to general problems. But in graphics programming, you always start to copy-paste shaders and the corresponding glue code to make small adjustments because you structured your program slightly different. So I wanted to give everything just enough structure to allow for reusable components without restricting everything too much. In summary, I wanted something that 1. Lets me focus on algorithms and data structures and does not bother me with buffer management, semaphores, fences, and so on. 2. Something that enables building reusable components by giving the applications just enough structure without being too opinionated on how to do things. And 3. I want something that is easy to pick up and where simple things stay simple without being too restrictive. And after 3 years I can say it's difficult. But I want to show you what I have got so far. Everything started when I built a transpiler that allowed me to share code and data structures between Rust and shader code. I combined that with a more or less traditional ECS architecture to give everything enough structure while remaining hopefully flexible enough. For those who don't know what an ECS architecture is, I have some articles linked below. But here's a quick wrap-up. ECS stands for Entity Component System, and it describes an architecture for often games, but also other applications. The application state is encoded using entities, which are just unique identifiers, most often some number. You can attach components to these entities, which are general data structures and can be anything. The behavior of the application is then defined using systems, which are just functions which can read and modify the entities and components to implement the desired functionality. Let's have a quick look on my implementation. If you are already familiar with the ECS architecture because you used Bevy or any other implementation, go to this timestamp to get to the interesting bits. So let's have a look at this very first example. Here we have a single system, which is a function with no arguments, which just prints hello world. Here in the main function, the entry point of the program, we create a new application, register the default Ovis module, more on that in a later video, and then register our system. Then we run the application, which basically calls every system in a loop. So, to no surprise, we just get a bunch of hello worlds. This was quite boring. So let's make it a little bit more interesting this time. In this second example, we still have one system. However, this time it has a query parameter. You can think of a query like a database query which retrieves all entities with certain properties. In this case, the entity ID, which all entities have. Then we iterate over all entities within this query and print its ID. Down here in the main function, we have one additional step. We initialize the state by spawning 2 empty entities. And when running this example, we get a similar result. However, now each entity gets greeted individually. So far so good, but let's start using components. In this example, I created a name component, which consists of the first and the last name, which are both strings. We still have one single system with a query parameter, but this time the query yields all entities who have a name component. Then we again iterate over all entities within this query, and we can now give a more personalized message. Down here, we also changed the initialization of the state. We spawned 2 entities with 2 different name components and then an empty component at the end. Let's have a look on what happens when we run the program. As you might have expected, we get 2 messages greeting each of the entities. Notice that we spawned actually 3 entities, but only 2 of them have the name component, which is why this query only yields the first 2 entities. We can change this by making the name component in the query optional. Then this query will yield all entities and we can test whether it actually has a name component or not. So for the same initial state, we get the following output. Here you can see that we, like before, have the 2 personalized messages, but also a hello stranger for the 3rd entity. Until now, everything that I have shown is nothing new, and most ECS implementations support similar functionalities. However, the next example contains a special kind of system, a render system. In contrast to traditional systems in an ECS, the render system runs on the GPU and requires 2 functions. A vertex shader that assigns positions and other attributes to all vertices of the mesh, and a fragment shader that defines the color of its surface. Here you can see an example of a vertex shader that assigns each vertex the position of a triangle based on its index. The corresponding fragment shader assigns a constant color to the surface using the RGB function I defined. The GPU attribute on all these functions instruct the Ovis framework to generate the corresponding shader code and allows them to be executed on the GPU. Registering a render system requires additional meta information, like which render target to use, whether to fill it with a certain color before rendering, or how many vertices to draw. I don't want to go into detail here, as the syntax is currently a little weird and I'm in the middle of making it easier to use. Instead, let's look at what happens when we run the program. As you might have expected, we see a triangle with a constant color on top of a solid background. This in itself is not super impressive. However, when taking into account how much code we wrote compared to traditional Hello World programs using Vulkan, DirectX 12, Metal, it's not too bad, I think. But being able to do simple stuff with very little code is not worth anything if the solution is not flexible enough or if it gets complex too quickly when extending the program. I don't want to go into too deep in this video, but let's at least have a look on how we can use components within a render system. Here I added a triangle component that defines a triangle's visuals like position, color and size. I can then read this component from the source entity within the shaders to adjust the position of each vertex and set its surface color. Like queries in normal systems, the render system will iterate over all entities with the used component and emit a corresponding draw call. Here I spawn 3 different entities with slightly different positions, colors and sizes, which is reflected in the output of the program. I have to admit, these examples were not extremely exciting, but I hope that I at least got my general idea across and maybe sparked some interest. While the framework is already capable of more, it is not where I want it to be yet. I want to use these videos to build slightly more interesting demos each time and explore its capabilities and limitations. And if you have anything you want to see, let me know. And before you ask, the framework is not public yet, as it's very much work in progress. It is not yet ready to use, and I add breaking changes so often it wouldn't be fun. These videos are one way to hopefully keep me motivated, and if you want to support me, drop a like, subscribe and share this. See you soon.